This video series is designed to inform the viewer of the theoretical and practical experiences and innumerable variables that come when designing with polymers and other substrates in a vast number of materials, end-use applications, and plastic conversion processes. Bixby's R&D and product development team has decades of theoretical and practical experience designing with polymers in a myriad of processes, products, and end uses. In this video, we will assume the individual layers of a functional sheet or laminate construction have been properly specified for the end use. Here we will focus on the bonding mechanisms occurring between the substrates. When two substrates develop a chemical bond, usually they tend to have stronger peel strengths than just a mechanical bond. The strength of the bond will vary depending on the type of interaction created at the interface. The interactions that can develop at the interface are diffusion, co-crystallization, van der Waals forces, hydrogen bonding, and/or covalent bonding.
Adhesion is mostly controlled by the chemistry involved. For example, when we use ethylene vinyl acetate as a tie layer to bond to a polyethylene film, at the polyethylene interface, there might be some kind of a chain molecular entanglement because of the diffusion of the polymer change that might create some van der Waals forces, and co-crystallization of the back bonds can occur.
These two polymers adhere well due to chain entanglement, whereby polymer chains diffuse into the other material and become entangled. To achieve this entanglement, we require the polymers to be in the melt state, be compatible or have similar chemistries, and have sufficient contact time. The ability of these polymers to diffuse is related to the wettability of the materials as previously mentioned. Good wettability comes with polymers having similar surface energies and being compatible. Another type of interaction that helps with the bond of these two polymers are van der Waals forces and co-crystallization.
Van der Waals forces are a weaker interaction but are still important. These forces result from the small dipoles that exist in all the molecules and requires that the polymers have some proximity to suffer this effect.
If polymers like EVA and LDPE have enough diffusion, co-crystallization can occur. This means that the polymer chains can create highly organized lamellas, think of layering, that further improve the adhesion between these two. There are a few variables that we can control to improve diffusion during the extrusion lamination.
We can use a higher melt flow index, or in other words, reduce the viscosity of the polymers so the polymer chains have more mobility to freely flow and diffuse between each other. Increasing the pressure, the temperature, or the time in which the substrates are in contact will further improve the adhesion.
Similarly, the variables of time, temperature, and pressure can have beneficial effects on the other bonding forces as they're increased by allowing greater molecular interaction. Another type of chemical bond that can be developed at the surface of two substrates is, for example, the hydrogen bond.
Hydrogen bonding is a strong dipole-dipole interaction which occurs when a positive end of a group is attracted to the negative end of another group. Polymers with carboxyl, acids, amines, amides, or hydroxyl groups can therefore create hydrogen bonding with other polymers. We may have this type of interaction, for example, when we corona treat a polyethylene film that develops a carboxylic acid group on the surface and reacts with the oxygen of a urethane tie layer.
Covalent bonds are the preferred form of adhesion, as they typically provide excellent adhesion since they require significant energy to break. Although these are more difficult to see in the extrusion lamination process, covalent bonds can result from the reaction that occurs between the functional group in the tie layer and the bonding substrate.
For example, the anhydride group of the maleic anhydride modified LDPE reacts with the EVOH polymer, forming a covalent bond.
To give you an idea of polymer adhesive force strength, here is a table with the corresponding energy. The ultimate success of an effective tie layer chemistry is to create a meaningful laminate that won't fail or delaminate in the field. This emphasizes why it's so important to partner with a company like Bixby International, the custom thermoplastics sheet extruder and laminator with more than 140 years of knowledge and experience. In our next video, we'll discuss actual tie layer chemistry. This and other videos will be available for viewing in our video library at bixbyintl.com.